2018 for your response number one. Let's do it. So I like this question. This is taking us back to our days of linear regression back in the, I don't know, the fall, getting excited for, I don't know, football and Halloween and the fact that we got to learn together in a classroom back in those days. I definitely would prefer that were the case now, but nonetheless, so I like this question, right? You can pause the video and read it. Sorry, this is so tiny here, but of course, hopefully you already read this and tried it yourself, right? Definitely, do it first. So you can pause and read there, and we got this little, tiny font, or if I scroll down here, right? Like now you can pause it again or something and check those out. So I like this question because we're going to use it to really cover like a lot of the fundamentals of regression, just kind of a lot of the basic skills, interpret slope. Well, that's not in the question, but we'll do that. Interpret slope, y-intercept, r-squared, talk about outliers, look at a computer output, how to write the equation, identify slope and intercept. So this is a good little quick review question. So we've got this context here. We're looking at two variables, right? Two quantitative variables if we're working with a scatter plot. We've got a random sample of 11 customers. You might think about, not on this year's exam, but right, we could do t-tests and stuff with slope, so this would apply to our conditions, but that's a tangent for now. So as soon as each customer got to the end of a checkout line, they wrote down or recorded the number of customers in line who were in front of them, and then the time in seconds until that person finished their checkout, right? So I get in line, we look how many people are in front of me, and then as a result, how long does it take me to finish my checkout? So customers in line versus time to complete the checkout. All right, we see a fairly strong positive association here, pretty linear. We've got three things to try to address. So we got to identify and interpret in context, of course, the intercept for the least squares regression line. We've got to interpret the coefficient of determination, r-squared. And then we have to, this says 1 point was determined to be an outlier, circle the point on the scatter plot and explain why. And hopefully as soon as you looked at this, some point was jumping out at you as a potential outlier. And then we'll also interpret the slope because, why not? So let's jump right in. Let's not jump, let's jump back out. Before we do that, so when we look at this, right, when we look at our computer output, we need to be able to identify the slope and intercept and ideally write an equation, right? We're gonna have to write an equation like the predicted number of customers. Whoops, sorry. That's X, not Y, right? That's my explanatory, not my response. That's what I get for being lazy. So we're gonna have our predicted time to complete the checkout is equal to, so our slope, right? If we think about our days of, right, mx plus b, right? Now, that's not the form we typically use in stats, but we all think about that from our algebra days, right? So the slope, the slope is the coefficient to the x variable. So when you're looking at one of these, the slope is the coefficient to the x variable. And in this case, the x variable, the explanatory is the number of customers in line, or the IV, right? So the coefficient to the number of customers in line, right? That number right there is our slope. And then if we think about our algebra 1 equation over here, this constant, right, the number by itself, this constant is our y-intercept. So this right here is going to be our intercept. That's this kind of how you logically read that. The rest of the stuff we don't need. This comes up when we get into t-test intervals for slope, which is not on this year's exam, right? And then that would relate to a lot of this other information. We also see down here, this is the standard error of the residuals, and we see r-squared, right, which we're going to have to use in part B. I should have used a different color, so the green was just my y-intercept. So now we know the y-intercept is 72.95. So let's interpret that. So for a y-intercept, like I tell my students, right, like in any math class, right, how do you find a y-intercept, right? Like we got to do that for all the functions. So the y-intercept always occurs when the x value is 0. Right? We know that from back to our days of algebra 1, just graphing a linear function. So what this is saying is the y value is 72.95 when the x value is 0. And to interpret the y-intercept, right, now we just got to change the x and y to context. So this is saying if the number of customers in line is 0, right? There's no one in front of you. I shouldn't say customers in line because I guess technically they're right, but the number of customers in front of you in line is 0, right? So the number of customers equals 0. Then your predicted, your Y value here is the time. Your predicted time to complete your checkout is 72.95 seconds, right? A little over a minute there. So if we look at that kind of green and red and purplish, that's our sentence, right? When the number of customers in front of you in line is 0, the predicted time to complete your checkout is 72.95 seconds, something like that. So let's write it up. I'm going to try to write this. So we always want to specify that what the statement we're making is just a prediction from this one model, from this one random sample of 11 customers, right? This may or may not be true, right? In general, right? That's what we need statistical inference for. So to always make sure that I'm going to hit that idea that our model is providing us with predictions or estimates, I like to start my sentences for slope, intercept, and stuff with the model predicts right off the bat. So I got that. That when the blank is 0, the predicted, and now when I talk about the Y variable, right, I'm kind of overkilling the predicted part, but right, better safe than sorry on the AP exam. The predicted blank is blank. So in this first blank right here, right, the Y-intercept is when our X variable is 0, so that's going to be our X. The Y-intercept, right, is the value of Y. So this is going to be our Y when X is 0. And right, this is going to be an interpretation of that number in context. So you can try to use that general structure for most of these. So when the number of customers in front of a person in line is 0, the predicted time to complete checkout is 72.95 seconds. Right, and that's it. Now, sometimes, oftentimes I should say, the Y-intercept does not have a realistic interpretation in context. Like sometimes we say things like, in the year 0, the predicted population of whatever, Plainville, Connecticut is negative 50 million, right? That makes no sense. And so if we have a statement that doesn't really make sense, we should comment on that and say, hey, this is unrealistic, right? Can't have negative people in the year 0. Here, right, like, yeah, this is totally realistic, right? This just means I walk up and it's my turn and it's going to take some time to check out, so I don't really have to say anything there. So that's it. So let's check it out. Let's see. Essentially correct if we've got the right number as the Y-intercept. Got that. Communicates the concept of Y-intercept in context with both time and 0 customers. So we have the time and the 0 customers. Indicates the values of prediction using language such as predicted, right, estimated, average, right? So that's why you see me doing that stuff. So we got essentially correct. Pretty much it. You can pause and check out some of those other notes. Moving on to B. So now they asked us to interpret R squared. So the coefficient of determination, right, that's R squared. R squared, I can't really logically arrive at that the way I did with the Y-intercept. So R squared is giving us the percent of variation in the Y variable that can be explained by changes in the X variable, right? It's the percent of the changes in the time to complete your checkout that can be explained by the number of customers in front of you in line, right? And it's not 100% because what else would call it, or what else would help to explain changes in your time to complete your checkout? Maybe like, I don't know, who your cashier is or how many items you bought, right? So that's why this R squared isn't going to be 100%. So the model predicts, right? I'm just kind of getting robotic. I like to do it for all my writing, my interpretations with regression, always to hit that number 3 we just saw in it for essentially correct. That, or whatever, predicts about 70, right grammar here, predicts that about 73, and I would use like little squiggles for approximately 0.33% of the variation, or maybe you say changes in, right? Variation, changes, same thing. So about 73.33% of the variation in time to complete checkout can be explained by, we could say the model, right? The linear model is explaining that relationship, or we could say changes or variation in the number of customers in line. That's it. If you want like a more in-depth explanation of like where this sentence comes from, I strongly recommend the AP Stats Guide video on R squared. It's to me like the best interpretation video of R squared I've shown in class. So If you're like, hey, where did that sentence come from? Check that out. In general, for writing the interpretation of r squared, right, we could do this pretty generically, right? That's going to change. You're going to fill in that blank. That's just going to be r squared. This would have been a much better way for me to do this also on y-intercept. Right, this is always going to be your response, and this is always going to be your explanatory, right? So you could pretty much, not pretty much, you could write this exact sentence every single time, right? And you're going to be good. This is always just r squared, right? This is going to be your response variable, your y variable, and this is going to be your explanatory, your x. That's it. So let's see. Got the right number. We didn't pick that r squared adjusted. Correct, possibly generic interpretation. Ours is correct, but we don't want generic, right? We always want that context. We're using a generic structure, but it allows us to infuse context into it. See any notes down here, right? You could just see, I just like to show this. This is just a lot of different ways you could say this. So I would definitely pause and take a look through here. And beyond that, these are incorrect. So check those out. All right. So hopefully immediately when you saw this, right, 1 point jumped out at you, right? One of these looks like it's an outlier, and I'm pretty sure that all of us are going to circle this point, right? Outlier outside the general pattern, the general trend we see. Could say high leverage or high residual. So explain why. So the circled point is an outlier. So make sure you circle it. If you didn't circle it and you wrote the coordinates, like I think you could get away with that. I'm pretty sure we'll see in a second in the rubric. But like, why do that? Just circle it. It's way easier than writing the coordinates. So the circle point is an outlier because now the thing is when we write this, we're comparing this point to all the other points. So we can't just talk about this one point. We have to compare it to the others, right? Got to talk about in relation to others. So one reason, right, like this point is like far away from the line of best fit compared to the others, or I should say further away from the line of best fit than the others. Well, when we talk about that vertical distance, right, the distance from the point to the LSRL, right, that's our residual, right? Visually, this is the residual, except it's supposed to be vertical. Mine's terrible. So here, one thing we could say, there's a couple ways you can answer this. Because we could say the point has a higher residual or a high residual compared to the residuals of the other 10 points. That's one way to do it. Another thing you do is you could kind of just say like, for an x value of 3, we would expect the point to be, right, higher, like up here, right, where the cursor is. So the y value, we could say the y value is much lower than we would expect based on the model, something like that. So there's a couple ways you could say it. Nothing really crazy here. I think this is something we should all feel pretty confident about on the exam. So to get essentially correct, got the right point as the outlier. That's probably the easy part. And then we need describes an unusual feature relative to the remaining points, right? So that's that element of comparison I was referring to. So we could say the combination is unusual. We said the value of y is much lower than would be predicted. We also, right, looked at this, the residual is large relative to the other residuals, and we did do that. Check out these, right? I like this again, right? That comparison, that's the worst underlying ever, has to be there. But you can check that stuff out. Those notes, right? I think it's easy for us oftentimes. I should have said this like 10 videos ago, to overlook those and be like, whatever. Like oftentimes that's the most valuable information for you, knowing what can and can't be done in the exam, right? For a teacher, some of this is the most valuable information for me, right? For now, right, I'm just trying to hammer the essentially corrects, right? Because we're trying to get our 5s. But to get to that point, you have to know, right, how to write these things or how not to. So don't skip the notes, yo. All right, we weren't asked to interpret the slope, but let's do it. Why not? So the slope, I'm gonna go to the whiteboard. Just, why not, right? Why not read my sloppy, horrible handwriting and this shadow right here? So the slope, remember, we're looking at a scatter plot where we have the number of customers in line, and this is our time to complete the checkout, right? We saw that positive trend, and our slope is 174.4. So when I'm in class, right, I'm like, hey, slope, what does it mean, right? And this is something you probably did in algebra. And I say, what do you know about slope, right? And everyone says rise over run. Like, sure, okay, what's that mean? So then that's the change in y over the change in x, right? Slope is a rate of change. It's how our y variable is changing compared to how our x values are changing. So now we just want to translate the x and the y to context, right? So x, our x variable, is the number of customers in line, and the y variable is the time to complete the checkout. And then lastly, we throw in the number here. So the slope is 174.4 over 1. And so if we now just focus on like this box, this is our sentence. This is how the time is changing. This is how the number of customers are changing. The time to complete the checkout is going up because this is a positive number. We're really always going to view the positive or negative in the numerator, right? So this is always going to be a positive in the bottom. So we're going to say when the number of customers in front of you in line goes up by 1, the predicted time to complete your checkout goes up by 174.4. So slope is not something you just have to like memorize. It's something that you can logically arrive at based on what you know about slope. So I'll just write it out since this is here. So the model predicts as the blank increases by 1, the predicted blank either increases or decreases by blank. So here, our model predicts, did a pretty bad job at the lighting there, huh? And this is always, all right, our x variable is always going to be increasing by 1. So this is going to be as the number of customers in line increases by 1, the predicted time to complete checkout increases by approximately 174.4 seconds. Wait a second. Did I use the wrong number? Hold on a second. Oh no, I didn't. All right, cool. Sorry. I freaked out for a second right there. I thought I used the y-intercept by accident, but I didn't. My bad. That's it. Now, there's like better ways to say this. The model predicts that if there's one more person in front of you in line, your predicted wait time is going to go up by 174.4 seconds. That's probably a little less robotic and less, more like how we would talk to somebody. But I was trying to write this in a form where you could use the same kind of general structure and fill in the blanks, right? But again, it doesn't have to be these words, right? Model predicts as the number of customers in line goes up by 1, predicted time to complete checkout goes up by 174.4 seconds. And that, I think is it. Let me see. Did I slip anything else in this slideshow here? I don't think I did. We already went through all those. That was me making sure I used the right number before. I didn't. That's it. We're done. So one more 2018 to finish, and then it's on to maybe the timed practice exams that College Board put on their YouTube page, and then maybe if you're getting crazy and you want more, start working backwards, 17, 16, and so on. All right, everybody.